Day 2. Welcome back to the stream, everybody. So I'll probably just copy day 1 into day 2. That seems to make the most sense. See what the problem is. Okay, now you need to figure out how to pilot this thing. Wait, we don't know how to pilot this thing? We're already in the sub. Seems like the submarine can take a series of commands like forward 1 down to up 3. Forward increases the horizontal position by X units. Down increases the depth by X units. Up decreases the depth by X units. So we just have X and Y, up and down, forward and back, hopefully. Note that since you're on a submarine, down and up affect your depth, and so they have the opposite result of what you might expect. I don't like that at all. Can you just, can you please just tell me down goes down and up goes up? I would really prefer down going down and up going up. Already has a planned in course, your puzzle input, you should probably figure out where it's going. Forward 5, down 5, forward, whatever. Okay, cool. Horizontal position and depth both start at 0. The steps above would modify them as follows. Forward 5 adds 5 to your horizontal position, total of 5. Down 5 adds 5 to your depth, resulting in a value of 5. So we've just flipped the x-axis so that y, positive y is down. It only shows positive values here, even though there is up and down. I'm not gonna lean on the fact that that's all we have, positive values. Input, this is our input. So we read the string, input.text. We unwrap because if we can't get input.text, we just want to fail. I could make that nicer. I'm probably not going to. This is probably not something we need to call at the moment. So yeah, I'm thinking that we want to do buffered lines for this later, but I think I'm going to do that as an optimization. I'm just going to read everything and parse everything to start with, because it'll result in a little bit simpler code. And I'm a huge believer in writing the simple stuff that works. And then when you need to, doing performance work, taking things from owned to references, taking things from many allocations to fewer. What do you get if you multiply your final horizontal position by your final depth? Okay, so should we do it like this? Struct submarine x I32 y I32. So we want integers. We're going to do 32-bit signed integers, so we can go negative. We should just do an enum. Enum direction. Forward I32, up I32, down I32. Is there there's no backwards, is there? There's no like position. I guess position is going to be part 2. I do have my coffee today. Also, check this out. Ready? Take a bold away. We got a little comment highlighter now. So if y'all have, oh, you know what? I should have done that for the Rust question. I'm slipping. You got me slipping. Okay. So forward 5, down 5, forward 8. So we're only adding to the horizontal position. We don't have like a direction yet, like a backwards. So we'll do that. We'll do file.lines. I forget if folder reduce is the one with the initial state. So I'm going to impl default here. I'm going to impl default here. I'm going to derive default here. I forgot how much streaming just like messes with your head. Like simple things, like very basic things are just like, what am I doing? Cargo, let's just run. Cargo run. In part 1, expected closure that takes 2 arguments. So this is what the accumulator and the item, we'll call it. This has to return the accumulator, and then this will just do nothing at the moment. So let final position equal file.lines.fold submarine default. Default for integers is 0. I already know that, so we're gonna get a submarine at position 0, 0. Impl default is really nice. I really appreciate the fact that Rust provides a trait that lets you provide default characteristics to a struct or something like that. So if you need to construct one and it has valid 0 values, you can impl default. If it doesn't have valid 0 values, like you can't initialize it without setting things, then don't implement it. And you can write whatever new function you want. Okay, so there's this. Let's do mute accumulator item.split. Can we split on a character? I'm assuming we can. I should just use nom here. We'll do that later. We'll do it as an optimization. I have like a rock in my sock. Item.split. What does split return? Is split an iterator? I can probably just figure that out. Let things equals this. Turn my inlays on. But split car. I don't really want to collect this into a vec, but I'm going to for the moment. So we'll do match items 0. This is going to be a little bit awkward because I don't have the enum implemented yet. It's fine, but I do want to do nom because that'll clean this up a lot. I just want to show like the basic way to do it, like the split, and then we can move into something a little bit more complicated that cleans up this code a bunch. To act should we have a function called forward? Let's just have a function called move. Well, so the thing that I'm thinking about right now is, should I do the abstraction because I feel like I'm going to need it, or should I not? And I'm just not going to do the abstraction. And then let magnitude equals items 132. So we're using turbofish syntax. I'm just going to assume this works, because if it doesn't work, we're in pretty big trouble anyway. I have so many errors. Let's do this. I'll have to move that in a second, but that's fine. Why is collect yelling at me? Method, not a field. Oh, I didn't call it. Does plus equals not exist there? Oh, right. That's actually plus equals magnitude pattern. Okay. So if we have anything else, we're going to panic because unhandled input I. So if there's anything that's not forward, up, or down, we're just going to fail, because that means that we did something wrong, because this is a structured problem with clean input. Ooh, totally forgot that enums could take a values last night. Yes. The fact that structs and enums together form like sum and product types is one of my favorite things about Rust. You can stick structs and enums together with data, and it's so nice to just have this thing that's like forward plus this amount, or forward plus this data. And anyway, it's one of my favorite things about Rust. Oh, is panic a format thing? Yes it is. I think that there were recent changes to panic to bring it in line in Rust 2020 with the formatting behavior of the other formatting things. But okay, so all of this we need to do up. Let's just do this up here, because why do we need to do that 50 bajillion times? So up is going to be act.y. This is minus the magnitude. And then down is act.y plus magnitude. And then we just return the accumulator. Final position is not used. And then we can debug out the final position. Oh, because I don't have debug implemented on this. That'll be fun. Actually, I'll implement like display or something on that. That'll be fun later. 1998 and 741. Oh wait, what's the actual thing we need to do? Impl submarine finalize is what I'm going to call this. Function finalize takes a reference to self, returns an I32, returns self.x times self.y. I think that's what we're doing, right? So we can just finalize that now. And then allegedly this is our answer. Huzzah, 1 gold star. Okay. So let's review part 1 for a second, and then we'll move on to part 2. So what I did here is I built a struct called Submarine. Submarine has 2 fields, X and Y. X and Y are I32s, which are assigned 32-bit integers. Integers are nice because we don't have integers in JavaScript or something like that. JavaScript is all floats, which is, rough. We derive default and debug. Debug is just something that you should probably derive on everything. Default is something that you have to make a decision about whether you want to derive or not. Sometimes default doesn't make sense. So think about whether you have a default value. But if you do implement default, then we get to use submarine : default, which is the function for the trait, which is really nice. We impl submarine to add some functions to a submarine. Basically, if we are going to like finalize the submarine and do the thing that we need to do to finish the problem, we have to have a submarine. We have to have the X and the Y. So I'm just going to impl submarine, self.x, self.y, multiple of them. Enum direction is something that I want to use. So I wrote it down here so that I would think about it later. Where I want to use it is like right in here. The way I just wrote this is kind of like simple Rust is the way that I would put it. It's like much more like JavaScript or like something like that than you might expect, right? Like we have default here. Yes, like we have to put mute in front of the accumulator so that we can actually mutate it. But this is really just like split, collect. We have like an array of 2 things, parse one of them into an I32. If these strings match, then do a thing. If not, then we totally messed up. and then just return the value. Like this is fairly, I would say, standard code for a language that doesn't have enums, that doesn't have really good parsing support, that you might do this with regex in another language instead of doing split. But yeah, so I don't mean like simple as in easy. I don't mean simple as in like trivial or anything like that. I mean simple as in like, it's probably what you expect. So instead of simple, it's probably what you would write if you had no experience with Rust, but you had experience with like JavaScript or Ruby or something like that. And because we impled on Submarine, this final position is a Submarine when we return. So you can see that with the type inlay here. And then we finalize it to get the multiplication. So it's fold like reduce in JS. Rust has fold and reduce. So the thing that these are on is called an iterator. Iterator is a trait. It's the thing that powers for loops in Rust. It's the thing that powers map and everything else. So fold lets us initialize an accumulator and then gives us like the first value and the second value and the third value. And then we have reduce, which allows us to treat the accumulator as the first item in the iterator. So for fold, we get our initialized value and the first item for our first iteration. For reduce, we start with the first and the second item. So we have both. We have options. Choose which one works for your case. Based on your calculations, the plan course. So this is part 2. I think we'll do part 2, and then we'll go back and we'll optimize part 1. I think that's the way that I'm gonna work my solutions here. Based on your calculations, the plan course doesn't seem to make any sense. You find the Submarine manual and you discover that the process is actually slightly more complicated. In addition to horizontal position and depth, you'll need to track a third value, aim. So a theoretical z-axis, I guess, which also starts at 0. The commands also mean something entirely different than you first thought. Down increases your aim by X units, up decreases your aim by X units, and forward does 2 things. Increases your horizontal position by X units, increases your depth by your aim multiplied by X. I'm gonna probably trip up on the wording of that, but we'll keep going. Note that since you're on a submarine, down and up do the opposite of what you might expect. Down means aiming in the pot. Why? That's still like, why do we need that to happen? Why can't we just match like what we would expect? Why do we need to randomly flip up and down? Now the above example does something different. Forward 5 adds 5 for a total of 5. So I'm just going to start out by copying the other stuff that we have over here into part 2. I do kind of want to keep the dhat stuff, so I'm going to copy it down here and then move stuff around a little bit. You know what I should do? If we have enough time later, I should do a cargo generate template that has just like dhat in part 1 and part 2 and a library function. In our submarine, we're also going to have aim, which is probably also going to be an I-32. So based on your calculations, the plan course doesn't seem to make any sense. You find the submarine manual and discover the process is actually slightly more complicated. So down X increases your aim by X units. So down increases aim by X units. Up X decreases your aim by X units. So these are both operating on aim now. Forward X increases horizontal position by X units, and then increases depth by aim multiplied by X. So let's start with increases horizontal position by X units. Already do that. Increases depth by your aim multiplied by X. So act.aim times magnitude, and this is act.y plus equals that. I have a really good idea for doing this later when we refactor a little bit. Let's see. Should we just run it and see if it works? What are the chances that just by making 2 changes, it just works? Huzzah, we're done. We're not done. We're going to refactor, but problem 1 solved, problem 2 solved. So it was just a couple of logic changes for all of the ups and the downs and the figuring stuff out things. Let's go back to part 1. I think what we're going to do here is we're going to start using nom, and we're going to parse into enums, which I absolutely love doing. And then what else are we going to do here? Yeah, nom to parse into enums, which will make this a match on enums. We should probably dhat this before we do that and see what it impacts. Again, I don't really feel like the runtime is really interesting here, so maybe we don't do criterion today and we stick with dhat. So dhat allocator, standard FS, and then the thing here. So I'm just dropping in the dhat stuff. So we can now compile with release. So cargo build release features dhat. And then I want to target release part 1. And I'm going to copy this. So I would like to change this. The split feels very funky to me. It doesn't feel very rusty. It doesn't feel very, we're not really handling any errors. We kind of defer our errors to like the parsing, and then like we don't know here if we actually covered the entire input. So I want to try to do that. And then the other thing that I want to try to do is do all of this incrementally, because we can just read the whole thing down the line and we don't actually have to keep it in memory. So I think that's going to have a larger impact on our total. Interestingly, both of these allocate the same amount of heap. I guess because we don't really do anything that different between them. So let's start with doing a read line by line in, which I forget exactly how to do. So Rust, read file by lines. I don't want to use dot lines, right? I want to use a buff reader. I want to use like a buffered read on the file. So we are looking for read lines, and then we consume it. We're going to drop this in. This is going to be file name. We're not going to read to string. We are going to pull in file. So standard FS file. We are going to pull in IO. We're going to unwrap this because we don't have error handling at the moment. We are going to not return OK here because that's not something that we're doing. And this overall is the thing that we need to do here. And then method not found in buff reader file. So we didn't pull in a trait is what I'm thinking. Let's go check the imports here. Pull this in. I don't know why Rust Analyzer suddenly stopped merging my imports, but I find it a little bit awkward. Method cannot be called on a result string IO error split. So our item, so when we do read, I assume we get the chance to handle every, yeah, okay, so we get the chance to handle every error or every line as a potential error. So we are going to completely bail out of that at the moment. I guess that's the wrong thing. Did I read the message wrong? Item.split cannot be called on result string IO error, which makes sense, right? So if we unwrap the item, then we should have a string. Oh, temporary freed while still in use. That makes sense. We're just going to call it unwrapped. Or it's going to be Spotify unwrapped. Unwrapped equals this. So we're actually allocating more by doing this. Let's take a look at the, do I still have the dhat viewer up? No, I don't. Dhat Rust online version. That's what we want. We grab the file, heap.json. That didn't work. That's not what I meant to do. All right, so let's check out what's going on here. Total 2 blocks allocated at too insignificant, too furious. Okay, so 6,000 nanoseconds, 96,000 bytes in 3,000 blocks. We keep 8,000 in memory. I wonder, let me check the README again. Let's look at what we have here. We have 7,002 blocks. So I think allocating that extra string is actually hurting us. Okay, allocate. You know what, I think we should start doing criterion for these, because if we change the heap and we don't check the runtime, then we can have an effect where we grow the heap, but the runtime gets faster. This is also not a very large file, so I'm not even sure that matters. TGmax was 6,000 here. I didn't check the other one. I should have pulled this up before we did that. Dropped the JSON file in. So this is vec allocation from collect from iterator.rs on 33. So at 33 final position, I guess fold calls collect. Yeah, the speed memory usage trade-off is real. Yeah, for sure. Part 1 main closure, fold calls collect under the hood. Why are we allocating a vec though? I wonder if I write a for loop if this gets smaller. What's the example they use here? They use a for loop here. Buff read, reline, lines, iterator fold. So total is 8,000, but the max is 10 bytes. Max is 64 bytes. So I guess actually we end up using more of the heap total, but really what I should have done is checked the JSON file for the other one before I made these changes. So let's do that quickly. I'm gonna do stash. I'm gonna stash this part 1. We will load our JSON. I think our program runtime doubled too. So I think actually read to string and the Rust compiler already knows what to do here, interestingly enough. Because look at how small this is. This is one giant allocation for the fold. And this one, so the revised version is 2 allocations. So this is still 80,000 bytes. This is 87. And this is just 80,000? Where does the extra 96,000 bytes come from? Is a question I have. Like there's 80,000 here, and there's 87, 83 here, right? In the first one, there's 80,000 here, but it says 87,726. Okay, is it more interesting to y'all to do a nom parser here? I think we should do the parser. The dhat stuff doesn't seem to be leading us in a very interesting direction. The changes aren't very big, and we can just run this again anyway. So we are splitting collect here, and I think that getting rid of this collect is probably helpful because we are instantiating a new vec for every line. So getting rid of that is probably worth more time than actually reading this in line by line, because I don't think that leading this in line by line is nom, because I know nothing about it, and dhat is still very magic-y to me. Yeah, okay. Let's do nom then. There was just a new major, not just a new major version, but there is a new major version of nom. So I'm just going to copy the example straight in, and we can do for direction, I think is what we'll do. So I'll paste this down here. Cargo add nom. I don't think we need anything else. I do want to build this quickly because if we don't, then Rust Analyzer will just complain forever. Okay, so this is the parser. So let's do direction here, or move. Let's call it move, I guess. Maybe, I don't know. We'll find out. We're gonna pass back a direction. We are going to, what are we gonna do here? We're gonna do opt. I don't think we need any of these extra helper functions here. We're gonna do alt tag forward tag up tag down, and alt needs to be brought in, tag needs to be brought in. We're gonna do bytes complete tag. I believe this needs to be a tuple, so because these can be different parsers, it has to be a heterogeneous type, which is what tuples are. So this will give us forward, up, or down. We could write an additional helper function here actually for that specifically. But okay, so basically what I'm doing here is I'm taking the input. So move is our parser. We're taking a string slice. iResult is a nom specific result type that gives you the input type, the type that you're parsing into successfully, and then it kind of hides the error type from us. So we could define our own error type, but we aren't going to at the moment. But just know that there are 3 things defined in this type. There's the input type, which is a string slice. There is the thing that we are parsing into, which is the success return type. And then there is the error type. This is not what we need. This is not what we need. There's probably an I32 in nom. So let's go look for that. Yeah, let's just do I32. And then we're gonna have to bring this in, and it's not going to be from standard. It's going to be from nom. Magnitude. I think we have to pull in iResult too. We don't have iResult in yet. Well, adding nom, add more to the heap stuff you were looking at earlier. It should reduce it if we write it correctly. What are the alt and tag functions? So nom is a parser combinator library. This means that what we have is a bunch of functions that we can combine to build a larger parser. So in this case, when we say tag here, switch over. When we say tag here, we're looking for the string forward in the input. And what alt does is it says there can be one of these. So it can be forward, it can be up, or it can be down. And alt takes basically a selection of potential parser combinators. So in this case, it's just one of 3 tags, but it could be any number of things. And then we pass the input. So this constructs for us another parser combinator, basically. It is the parser combinator that will parse one of tag forward or tag upward or down. And we apply that to the input. So we pass the input in as a function, as an argument. And this will either succeed or fail, which we're handling with the question mark. The question mark will return through this iResult type. It's the same kind of thing that you would expect in any other question mark usage. In which case, we also have the input and some stuff we're ignoring. Actually, we're ignoring that right now, right? We'll call that dir to pull out. So what we get back from these parser combinators is the rest of the input and the value we parsed out. So we take, each time we're doing this, we're shadowing the input variable. It's just kind of a convention to do this because you have to write it a bunch. So this is the full input right at the top. We pass the full input to this parser combinator. This parser combinator gives us the rest of the input and whatever it successfully parsed out, which we can then use to do something like this. So we're basically, it's going to be forward space, whatever, right? So I'm going to try to tag a space and I'm going to pass in the rest of the input. And that will give us the rest of the input and whatever it parsed out. In this case, it's a space, so we're not actually going to use it, which we can then pass the rest of the input into our I32 parser, which will give us the rest of the input, and then the thing it parsed out. So all said and done here, what we have here now is the dir, which is the direction forward, up, down, and the magnitude. So if we match on dir and we get like forward, up, or down, so you can see that this is basically the exact same stuff that we wrote up here. Forward, up, down. But in this case, we're going to do direction, forward, magnitude. And instead of doing this down here, or let's call this result, and let's return result here. So you'll see that the function signature for all of these parser combinators is rest of input thing, right? So when we write our parser combinator, because move is yet another one, it's just one that composes like all of the others, we have to return the rest of the input and the result. And then we could do a number of things here. Nom locate and nom supreme are also very interesting crates. I think we'll cover those later. Nom supreme is really interesting. It allows you to keep nom supreme allows you to keep everything that happens and errors from the entire tree of parsing. So it gives you a lot more information. And then nom locate gives you like the point in the document at which you had got an error or got a value, which they call a span. So both very interesting, cool things, but I think we're going to keep it simple today. I think we're just going to unwrap this or whatever. Not unwrap. If I was trying to write production level code here, I would make sure that this came back as an error that I could handle. Why is move complaining? Oh, because move is a keyword, right? We can't use move. What do we call this? I'm just going to call it parse direction. It's kind of not how everybody, like you don't see this as being parse tag or this as being parse alt. It's just tag and alt. So people usually go that way, but we can do parse direction. So in here, we can do parse direction item, and I'm just going to unwrap this. We're going to throw away the input and just take the direction. So now we know we have a direction, which gives us all of the magnitudes and everything. Yeah, nom is super powerful. I think it's far more understandable than doing parsing in other ways. Like if you start looking at ASTs and you start looking at like how people are like, hey, this is how we do a compiler and whatnot, you'll start hearing about like Lex and Yak and like all of that kind of stuff. And that gets like super, I don't know, it's like super in-depth and confusing and like not where I would suggest people start with parsing in ASTs. Parser combinators to me, they are functions that return like things you can compose, right? So like when you have a function that parses something, it returns you a value and you can compose that with other functions to parse more complicated values. So for example, the nom docs start off with a hex color, basically, right? Like hash FF AABB kind of thing. And there's a tag and you compose this hex primary function. And these are all just functions that take string slices and return like whether they successfully parsed the value that they wanted to or not. So you get to write like regular functions and you get to compose those functions together, which is basically what we do in programming all the time anyway. And that gives you these like really high level parsers that give you rich structs and things like that. So we can match dir here now, and this will be forward magnitude, up magnitude. Okay, so we've got direction forward now, direction up, and direction down. And this is not something we need. So that cleans up our code quite a bit, because now we don't have to do this split thing up here. We don't have to do any of the other stuff. Let's build this and run it. And there we go. So 1480518. What was our answer for part 1? 1480518. So we're good. So not only are we good, but we brought down our total usage to 7,000 bytes. Like we were doing dhat before, right? We were looking at 80,000 bytes, and we were like, okay, maybe if we do it like line by line or something like that. But that didn't do much for us because the Rust compiler was already smart enough to realize what we were doing and basically do a better job than we were able to. But if we bring up the viewer for our new iteration here, and we look at the heap, we see that this is not only taking much shorter, so it's taking 161 nanoseconds, whereas the other two took what, 6,000 and 3,000, which, to be fair and be perfectly transparent, dhat is not a runtime execution profiling tool. It's not. We would be using Criterion for that. We should be using something else, a different tool for that. So it's really just like context, right? It's not, hey, this runs faster or slower. It's just context. But we can see now that we have a total of 7,000 bytes. So we got rid of the allocations for split, and that seemed to be the big problem for us in terms of allocations anyway. So we've got the 12 bytes for opening the file, right, for the read to string stuff. And then we've got 7,000 bytes for actually doing all of the work. Well, actually, is that true? 33 and 33. We don't allocate at all, actually. So nom makes it super easy if you're using the right types. To actually, we didn't allocate. Nom doesn't allocate anything here. It's a, what is going to be the term for this? Is it zero copy? It's zero, yeah. So I didn't mention this before, but the description of what nom actually is a parser combinatorial library with a focus on safe parsing, streaming patterns, and as much as possible, zero copy. And you can see that here. 1,000 bytes off with nom? No, 70,000 bytes off with nom. Or 90 if you want to look at this. So this is 87,726, and this is 7,726. So 80,000 bytes. It doesn't allocate anything because it uses references, Nikki. Like the types we're using here, the string slices, we're passing around references to things that are already allocated. We don't do any allocation here, right? So it's not like we're creating a capital S string, allocating more on the heap, returning this extra stuff. Like we're passing in a string slice, we're returning a string slice, and the only thing that we're doing here is pointing to references in pieces of that string. Yeah, nom is super impressive piece of software. Let me copy paste this into the README. Part 1 with nom. So what else do we have here? Really the only thing, oh, that's part 2. Really the only thing is like, instead of matching here, we could move this onto a function on the submarine. So instead of having this like this, we could have sub dot, we can't call it move. Sub dot, what's another word for move? Somebody give me another word for move. Swim. Our submarine swims. That's impressive. This is going to yell at me because I'm taking a mutable reference. Oh, let's just make this unit. We actually don't need to return this because it's muting. And this is sub, and then we return it. So now look at this, right? This still does the same thing. Build release, part 1, 7726. We have changed nothing effectively. So now all of our code is encapsulated into these like 5 lines, right? Or like the thing that we're doing is encapsulated into these 5 lines. We take the lines, we fold over the submarine. Let's get rid of the inlays here. Looks a little cleaner. We take the sub, we take the line. I guess we should call this line and not. We parse the direction out of the line. If we get one, we swim there, and then we have the sub. But yeah, so like we just move this. We're moving the direction in here. We do nothing additionally on the heap. So yeah, I mean like nom and Rust and trade implementations and things like that allow us to do a lot of like cleaner work here. And then like, So this is all basically the same stuff, right? So let's do this. Let's go parse direction. We'll pull it out. We'll put it into this library, right? I'm going to copy and paste all of the use stuff. We don't need FS here. We don't need dhat here. The submarine changes, so I'm going to leave it here. The direction does not change, so I'm going to pull it into the library, right? And we need to make the use pub. And then this is use, what do I call this? What did I call the day to submarine? No, day to direction. It's not crate because the crate is the bin. I think I need to define the library. Day to direction. What did I do here? Oh, it's named day one. Oh, no. No. Parse direction. We don't need nom here anymore. We do need that and whatever. So we've got our sub definition and what the sub should do in response to the things. We've got the main stuff. This could probably be pulled into. Okay, so if we look in here, we can pull in the same stuff now that we have an actual. So parse direction and direction. We'll get rid of direction here because it's the same thing. Parse direction. We need to redefine the sub. So if we take this, right, and we have this submarine here and we add the swim, but we move our logic back in. So we're changing the implementation of the submarine, but we're using the same direction and the same parsing mechanics. Oh, that's not sub, that's self. And then I'll go down here and I'll take this final sub stuff and I can just paste this right in here because it's the same exact thing. And now we've got this function, which we could use, right? We could define this in our library and just say, pass us a string of new lines and we'll deal with it. But I decided not to in this case. The only changes here are the magnitude. So if we build this and we run part 2, we get 7,726 bytes. So where's the README? So they're the same, but it is nice to confirm that they are indeed the same. So yeah, I hope that I've stoked your interest in nom because nom is absolutely freaking amazing. It's reasonably easy to use. I will caveat that with if you're trying to fully enumerate your errors, you are going to have to put more work into learning what nom does with those errors. You do have to map your result type into one that can be used in this iResult. This iResult is actually a 3-item type. So again, the string slice for the input, the output type, and the error type. The error type is not shown on screen here. You can put that in there, but that's the only caveat that I will have. I really love nom. Nom is really great. It makes it really easy to write really performant, really low allocation like parsers. I have an MDX implementation using nom that is, oh dang, it runs in nanoseconds. Yeah, I don't know. I absolutely love the way that Rust comes together in the sum and the product types, which allows us to do these like structured operations, right? Like we know that we have one of these 3 now. We don't have to just be like, oh, is there like an extra string or did I misspell this? Like, no, like we parse it, it either parsed correctly or it didn't. And then we have from that point on, just these enums with the data that they need. And then nom is just like mind-blowingly awesome when it comes to actually parsing stuff. So yeah,